Welcome to This Explainer. I'm absolutely thrilled you're joining us today because, well, we're going to demystify a topic that consistently confuses even the most seasoned data professionals. We are looking at two absolute titans of the data world, statistics and econometrics. Now, on the surface, they look incredibly similar, right? But as you'll see, they operate on completely different wavelengths. So let's get right into it.
To a layperson or, even a casual data analyst, both of these fields just look like people staring at spreadsheets, running regressions, and crunching numbers all day. You might honestly think it's just a matter of where they happen to work. Like, if you study agriculture, you're a statistician, and if you study the stock market, you're an econometrician. And that sets up the central mystery we're going to solve today. Are they really just the exact same math with completely different names? Okay, let's dive into this by first looking at the superficial differences. If you peek over their shoulders, you're going to see that statisticians often prefer pretty straightforward models. They use things like logistic regressions, they look for straight-line relationships, and they really value simpler variables. Econometricians, on the other hand, absolutely love complexity. They favor probit regressions. They look for curved relationships, like, say, how your income affects your life satisfaction completely differently depending on whether you're making 3 million or 10 million yen. They use these highly complex interaction terms, like the Heckett models developed by James Heckman back in the 70s. Honestly, it looks like a mathematical arms race. But here's the real secret. The real difference isn't mathematical at all. The complex math, all that heavy jargon, they actually distract us from the truth. The fundamental divide driving these two disciplines is profoundly philosophical. They're trying to solve the exact same mysteries of the universe, but they're approaching them from completely opposite directions. And to really grasp this, we need to understand two absolutely crucial concepts.
The first concept is induction. So induction is the process of gathering individual specific cases or data points to try and derive a general overarching rule. Think of a detective at a crime scene, right? They don't know the whole story yet. They are painstakingly gathering individual clues, a fingerprint here, a footprint there, to slowly, carefully build up a general theory of what actually happened. They are moving from the specific to the general. The second concept is deduction. Now, this is the exact opposite approach. Deduction is the process of starting with established facts or baseline assumptions, and then using strict logical reasoning to deduce a specific, broad conclusion. Think of a physicist. They start with the established law of gravity, and from that universal unbroken rule, they can deduce exactly how fast a specific apple is going to fall to the ground. They move from the general to the specific.
Section 1. Statistics, from cases to rules.
Let's explore the world of the statistician first. This is a world built entirely on that foundation of induction, going from those specific cases to general rules. The famous statistician C.R. Rao perfectly captured this. He said the development of statistics quantified the uncertainty in inductive reasoning, making it more accurate and bringing a major leap in our thinking. Modern statistics, which actually originally grew out of biological statistics, was literally invented to make this inductive detective work mathematically rigorous. It is essentially a tool to take a bunch of random data points and figure out exactly how confident we can actually be about a general pattern.
And because statisticians rely so heavily on induction, their whole approach is defined by humility. They really value having as few assumptions as possible because, well, a single bad assumption ruins the entire investigation. They focus purely on the sampled groups sitting right in front of them. You are rarely going to hear a statistician make a sweeping generalization about the whole world. They much prefer to say, hey, based on our data, this is true, but literally only for this specific group we studied under these extremely specific conditions. They are deeply, deeply cautious about applying their findings too broadly.
Section 2. Econometrics, from premises to conclusions.
Now, if the statistician is our cautious detective, the econometrician is our bold physicist. In this world, deduction rules supreme. And this brilliantly illustrates the foundation of deductive thinking, Isaac Newton. Newton obviously didn't measure every single object in the universe, right? He used deduction. He started with just 3 simple, unquestioned assumptions, his laws of motion. He assumed velocity is constant without force, force equals mass times acceleration, and every action has an equal and opposite reaction. And from just those 3 basic premises, he was able to explain the physics of the entire solar system.
Econometricians basically take this exact Newtonian approach, but they apply it to human society. They start with fundamental, almost unquestioned assumptions. Things like humans will always act to maximize their utility, or all economic activity fundamentally boils down to barter. They take these premises, stack them together, and use them to build massive, deductive mathematical models to explain the reality of entire nations.
And honestly, this explains why their math looks so completely different. Unlike the humble statistician who really just wants to describe a sample, the ultimate goal of econometrics is to build the most accurate model possible so it can be broadly applied to practically everything. They aggressively tweak their models. They use those curved lines, complex equations, and interaction terms we talked about earlier. Why? Because they fully intend to apply this model to millions of people, and even the tiniest error in their deduction is going to lead to massively wrong conclusions down the line.
So the crucial point here is, what does this actually look like in practice? Well, consider this massive number, 7 trillion yen. That's a huge number, right? This is actually the estimated annual economic loss from smoking in Japan. But think about it. How do we actually arrive at a number this huge? We obviously can't interview every single citizen. To get here, we actually have to use both philosophies.
First, we use the statistician's tool of induction. We look at health data from a localized sample group to induce the cancer risk of smoking. But then, the econometrician takes over using deduction. They assume that specific risk applies universally to everyone, they multiply it by the national smoking rate, then they deductively factor in future medical costs, the loss of labor, and a bunch of other economic variables to deduce that massive 7 trillion yen reality. They literally take a localized statistical finding and aggressively scale it up using deductive logic.
So, to summarize this definitive contrast, and if you're taking notes, this is absolutely your screenshot moment, statistics is all about induction. It's starting with specific cases to find general rules, using a really humble approach with very few assumptions. Econometrics, though, is about deduction. It's starting with bold rules and assumptions to build broad, sweeping models of society. They are literally trying to solve the exact same problems, just moving from opposite sides of the spectrum.
Section 3. Decision-making in the data era.
Let's bring all these abstract philosophies down to reality for a second. Why does this actually matter to you and your daily work? Well, it's because we are living in a fundamentally new era of data. The dense, intimidating math that used to separate these two fields, it's increasingly being handled by artificial intelligence. Crunching numbers, executing complex equations, writing analysis code, honestly, that is AI's job now. And this fundamentally shifts the value of human workers. Your job is no longer to just do the math. Your job is setting the objective, deeply understanding the assumptions being made, and choosing the right philosophical approach. In the modern workplace, it is not about the math you use. It's about understanding the assumptions behind your models and knowing just how reliable they truly are. You have to know exactly how to set up the problem. You need to look at a business question and decide, do we need the humble, inductive caution of a statistician right now, or do we need the bold, deductive modeling of an econometrician to forecast our future?
The tools have literally never been easier to use, which means your strategic thinking has never been more vital. So now that AI handles the heavy mathematical lifting, how are you going to use the philosophies of induction and deduction to drive your next big decision? Are you going to build from the ground up, or are you going to deduce from the top down? Just something to think about the next time you're staring at your data. Thank you so much for joining me on this explainer, and remember, always keep questioning the assumptions behind the numbers.